Our universe holds families of 9 suns dancing together. This is the staggering reality of nonuple star systems, and their existence breaks the rules of cosmic stability. By the end of this journey, you will understand 25 discoveries that reveal how such chaos is even possible. We will see planets with skies full of suns and witness stars stealing life from one another. How does a system of 9 stars not tear itself apart immediately? What would a sunset look like with 9 different points of light? The answers challenge everything we assume about order in the cosmos. What does it make you wonder about our own single sun? The first and most profound discovery is simply that they exist at all. For decades, the theoretical limit for a stable multiple star system was thought to be far lower, perhaps 4 or 5 members at most. The mathematics of gravity are unforgiving. Add more massive bodies into a chaotic dance, and the system should violently eject the excess or collapse into a series of catastrophic mergers. The idea of 9 suns holding together for millions of years seemed like a fantasy, a temporary fluke that nature would quickly correct. Then we found one. The system known as HD 98800, located about 150 light-years away, presented astronomers with an undeniable and baffling reality. Here was not a temporary cluster of young stars, but a mature, gravitationally bound family of 9. Its detection was a quiet revolution, forcing a complete rewrite of the rules for cosmic architecture. The secret to its survival lies in a concept called hierarchical ordering. Imagine it not as 9 stars swirling in a single, messy ball, but as a set of nested orbits. At the smallest level, you have tight binary pairs, 2 stars locked in a close embrace. These pairs then orbit a common center of gravity with another pair, forming a stable quartet. This quartet, in turn, orbits at a much greater distance around another grouping. It is stars orbiting stars orbiting stars. This layered structure minimizes close, destabilizing encounters. The gravitational fury is contained within each tier, allowing the entire sprawling system to achieve a precarious, long-term balance. It is a celestial ballet of astonishing precision, where chaos is meticulously organized into a fragile, enduring piece. This intricate layering leads directly to the second strange discovery, the architecture of the impossible orbits themselves. To understand a nonuple system, you must abandon any image of 9 suns circling a common center like planets around a single star. That arrangement would be violently unstable, doomed to collapse in a cosmic instant. The reality is far more bizarre and beautiful. These systems are organized into a precise hierarchy, a celestial structure so complex it resembles a set of gravity's own nesting dolls. Astronomers call this a hierarchical multiple system, and it is the master key to their survival. The chaos is not random, it is meticulously structured. At the very core, you find the tightest bonds, pairs of stars so close they whirl around each other in a matter of days or even hours. These are the fundamental binary units, the building blocks of the entire celestial city. Now imagine 2 such binary pairs, each a whirling duo. They do not merge, but instead, the center of gravity of one pair begins a slow, stately dance around the center of gravity of the other pair. This creates a stable quadruple system, a quartet of stars performing an elaborate gravitational minuet. This quartet itself can then become a single component in an even wider orbit, perhaps around another tight binary or even a triple star group. Layer by layer, orbit within orbit, the system builds upward to its full membership of 9. This hierarchical design is a brilliant gravitational hack. It confines the most intense and chaotic interactions to the smallest, innermost scales. The tight binaries handle their own fierce dance, while the wider orbits between groups are so vast that their gravitational pulls act more as gentle tugs, not disruptive shoves. This separation of scales is what allows the entire fragile edifice to stand across millions of years. Without this nested order, the system would tear itself apart in a relatively short astronomical time, a fleeting fireworks display of stellar collisions and ejections. The hierarchy imposes a strange peace upon the chaos, a set of rules that allows 9 suns to share a single cosmic address. This layered celestial architecture raises an even more tantalizing possibility. Could planets actually form and survive within this gravitational labyrinth? The third discovery suggests they can, and the evidence comes from the dusty cradles of planetary birth. In the very heart of the Nonuple system, HD 98800, astronomers have observed thick, swirling disks of gas and dust encircling some of the individual stars. These are circumstellar disks, the exact same kind of primordial material that coalesced into the planets of our own solar system. It is a staggering revelation that even amidst the complex gravitational tides of 9 suns, the basic recipe for building worlds is still at work. But the mechanics of such a world would defy all our earthly intuition. Stability for a planet here would demand an orbit either extremely close to a single star, safely tucked within its gravitational dominance, or incredibly far out, circling the entire chaotic ensemble. There is a narrow, precarious path between gravitational madness and serene order. Imagine standing on the surface of such a world. Your sky would be a permanent celestial festival. Multiple suns of varying brightnesses would trace impossible arcs overhead, some rising in pairs, others setting alone. Daytime might never truly end, just a perpetual, shifting twilight as different stars take turns dominating the sky. The concept of a single, steady habitable zone, that Goldilocks region where liquid water could exist, completely shatters here. Instead, the zone becomes a shimmering, moving target. As the stars complete their intricate hierarchical dance over centuries or millennia, their combined heat would wax and wane on any orbiting planet. This could create climatic seasons of epic geological scale, lasting far longer than a human lifetime. A world might bask in the gentle warmth of several distant suns for 1,000 years, only to slowly drift into a deep freeze as the stellar configuration changes, or be scorched as a close binary pair swings nearer. The very idea of climate becomes a symphony conducted by 9 different conductors, each following their own score, creating weather and seasons of literally astronomical variety. Could life ever gain a foothold in such an unpredictable environment, or is this the ultimate expression of a beautiful but barren cosmic art? This brings us to the fourth strange discovery, a cosmic scenario that makes the iconic twin suns of Tatooine look almost mundane. Within the layered hierarchy of a Nonuple system, a planet could find a stable home orbiting just one of the tight binary pairs. This world would have a pair of parent suns locked in their own intimate dance, while the remaining 7 stars become part of its extraordinary sky. Picture standing on that surface. Your primary suns might be a brilliant white and a deep orange, whirling around each other so quickly they could appear as a single, shimmering, elongated blob of light. But that is only the beginning of the show. Glancing across the heavens, you would see other points of brilliance, not as distant twinkles, but as unmistakable colored disks. A fiery blue star here, a cooler red giant there, each tracing its own slow, stately path against the black. True night would be a foreign concept. As one set of suns dips below the horizon, another might still be high in the sky, bathing the landscape in an eerie, perpetual twilight. The shadows themselves would be a spectacle of soft confusion. With light pouring in from 5 or 6 different angles, every rock and tree would cast a faint, overlapping fan of shadows, all shifting and merging as the suns move. It would be a world without sharp darkness, where the very definition of day is a fluid, ever-changing concert of light. How would life adapt to a reality where the sun never fully sets and the sky is a permanent gallery of stellar neighbors? The sheer variety of stars within a single Nonuple family is its own profound mystery. Our fifth discovery confronts us with a celestial menagerie, a collection of suns so diverse it defies the standard story of stellar birth. This is not a family of identical twins, 9 copies of our own yellow sun. Instead, these systems are cosmic melting pots. Observations have revealed Nonuple systems where a searingly hot, massive blue giant, burning its fuel in a furious rush, shares a gravitational bond with a faint, cool red dwarf that may shine for trillions of years. We have even detected the faint glow of protostars within these groups, infant suns still collapsing from their natal clouds, swaddled in dust and glowing with the heat of their own formation. This extreme stellar diversity is a critical clue, and it points to a violent, piecemeal origin. In a typical star cluster, siblings form from the same dense fragment of a giant molecular cloud at roughly the same time, leading to stars of similar composition and often similar mass. But a family containing both ancient red stars and newborn blue ones cannot have had such a simple, quiet birth. The presence of a still-forming protostar alongside mature stars is particularly telling. It suggests the system's construction may have been an ongoing process, a series of separate star-forming events perhaps triggered by the gravitational shock waves of the first star's birth. Or, even more dramatically, it hints that some of these stars were not born here at all, but were captured. The gravitational dance of the initial core group could have snared passing stars from a nearby cluster, pulling them into the complex hierarchy and adopting them as new members. This paints a picture of a dynamic, chaotic nursery, a place where stellar families are built through both birth and adoption over millions of years. The peaceful hierarchy we see today is not the starting condition, but the end result of a turbulent and dramatic history, a fragile order wrestled from profound cosmic disorder. The violent gravitational tides within these stellar families leave a clear and ghostly signature in space. Discovery 6 reveals the strange rings and debris belts that circle stars inside Nonuple systems, like the dusty structures seen in HD 98800. These are not the smooth, serene disks where planets peacefully form. Instead, they resemble our own solar system's distant Kuiper belt, a realm of icy leftovers and rocky debris, but one that has been thrown into utter chaos. The constant, subtle gravitational pull from not one, but 8 other suns acts like a perpetual cosmic stir stick. It prevents the dust and rocks from settling into orderly orbits, kicking them into elliptical paths that cross and collide. This results in a frenzy of constant, low-grade demolition. Asteroids and cometary bodies smack into each other far more often than in our quiet neighborhood, grinding themselves into vast clouds of fine dust and gravel. This relentless collisional cascade has a direct, observable effect. It makes these systems blaze with infrared light. While our eyes see the visible glow of the stars, sensitive telescopes detect the heat radiation from all that warm, pulverized dust. It is this brilliant infrared signature that often acts as a beacon, allowing astronomers to spot these complex systems across the galaxy. They are not just collections of stars, but stellar families surrounded by permanent, luminous halos of their own wreckage, a testament to the unending gravitational storms raging within. The relentless gravitational dance of 9 suns creates stranger fates than just dusty debris. Discovery 7 reveals a more intimate and dramatic stellar relationship, a process astronomers call stellar vampirism. This occurs within the tightest binary pairs at the very heart of the system's hierarchy. When 2 stars orbit perilously close, their gravitational embrace can become a one-sided theft. The star with stronger gravity, often a dense, aging stellar core, begins to siphon the very atmosphere of its larger but more diffuse companion. Rivers of superheated hydrogen gas stream across the void between them, feeding the hungry primary. In a calm, isolated binary, this is a well-understood, if spectacular, process. But place that same vampiric pair within the grand gravitational orchestra of a Nonuple system, and everything changes. The subtle, constant tugs from the other 7 stars can twist and warp the delicate stream of stolen material. They might periodically tighten or stretch the binaries' orbit, alternately fueling a frenzy of mass transfer or temporarily shutting it off. This external meddling can create bizarre, unstable feeding cycles, turning a steady trickle into a chaotic, on-again, off-again stellar feast. The evidence for this cosmic drama is written in the stars themselves, in the form of mysterious objects called blue stragglers. These are stars that burn hotter and bluer than their neighbors, appearing paradoxically youthful in a crowd of ancient suns. In a Nonuple system, a blue straggler is a prime suspect for stellar vampirism. Imagine an older star, its fuel nearly spent, beginning to cool and fade. Then, its binary companion drifts too close or is pushed closer by the gravity of the wider system. The aging star begins to drain fresh hydrogen from its neighbor's outer layers, dumping this new fuel onto its own core. This reignites its nuclear furnace with a vengeance, causing it to blaze with a hot blue light that belies its true age. It is a stellar resurrection, a second life paid for by the slow consumption of a sibling. This means that within these families of 9, we are not just looking at stars as they were born, but at stars that have been fundamentally altered, even reborn, by the violent intimacy forced upon them by their crowded home. The violent rebirth of stars through vampirism is just one form of energy unleashed in these crowded systems. Our 8th discovery listens in on a far more explosive symphony, one written in X-rays and radio waves. These Nonuple families are not just collections of light, they are roaring sources of high-energy radiation, cosmic lighthouses beaming out signals of immense violence. Observatories like the Chandra X-ray telescope have pinpointed these systems, and they glow with an intense, searing brightness that simple stars cannot produce. The source of this fury is a combination of youth and proximity. Many Nonuple systems are stellar nurseries, home to young, rapidly spinning stars that possess incredibly powerful and tangled magnetic fields. On a single, isolated star, these magnetic fields can snap, releasing tremendous solar flares. Now, place that same volatile young star into a tight binary pair within the Nonuple hierarchy. The gravitational pull from its close companion exerts tremendous tidal forces, stretching and stressing the star's interior like taffy. This constant gravitational kneading amplifies the star's internal dynamo, twisting its magnetic fields into even more complex and unstable knots. The result is not just a flare, but a superflare, an eruption of energy that makes the largest solar storm in our system look like a spark. These eruptions blast out vast clouds of charged particles at nearly the speed of light, which slam into the star's own atmosphere or the winds from its companion. These collisions are so violent they generate the X-rays that Chandra sees. Furthermore, the accelerated particles spiraling along magnetic field lines produce intense bursts of radio waves. In essence, the entire inner core of a young Nonuple system becomes a natural particle accelerator, far more powerful than anything we could build on Earth. The region between close stellar partners crackles with a permanent storm of high-energy physics, a continuous fireworks display of magnetic reconnection and particle collisions, turning what should be a peaceful celestial family into a cauldron of radiation. The brilliant X-ray glow and radio crackle from these systems act as cosmic lighthouses, but they illuminate a profound and unsettling truth. Discovery 9 forces us to confront the sheer, staggering rarity of Nonuple star families. In a galaxy brimming with over 100 billion stars, we have confirmed only a handful of these 9 sun systems. They are not just unusual, they are statistical miracles, cosmic needles in an unimaginably vast haystack. Finding them is one of modern astronomy's greatest detective challenges, not because they are faint, but because their light tells a story of such dizzying complexity, it can be almost impossible to decipher. The primary challenge is untangling the signal. From our distant vantage point, the combined light of 9 stars, many in tight orbits, blends into a single flickering point. This flickering can easily mimic other, more common celestial phenomena, like a single pulsating variable star or a binary system with a turbulent disk of dust. To see the truth, astronomers must become masters of patience and precision, collecting data not for months but for decades. They rely on 2 key, painstaking techniques. The first is called the radial velocity method. By analyzing the starlight with extreme precision, they can detect the tiny wobbles in a star's motion as it is tugged by its companions. In a Nonuple system, this wobble is not a simple back and forth, but a chaotic, multi-layered signal, a superposition of 8 different gravitational tugs. Separating that signal is like trying to identify every individual instrument in an orchestra by listening to a single, muffled recording from outside the concert hall. The second technique is even more subtle, focusing on the system's most predictable events, eclipses. If one tight binary pair within the hierarchy eclipses each other from our viewpoint, those eclipses should be as regular as clockwork. But when other, unseen stars in the wider system exert their gravitational pull, they can ever so slightly speed up or slow down the eclipsing pair's orbit. This causes the eclipses to arrive a few seconds early or late over years of observation. These tiny timing variations, called eclipse timing variations, are the fingerprints of the hidden companions. By meticulously mapping these minuscule delays, astronomers can infer the masses and orbits of stars they cannot directly see, slowly piecing together the full 9-member family portrait. It is a testament to human ingenuity, a decades-long pursuit to understand a cosmic configuration so rare it borders on the impossible. Yet within this apparent chaos, a hidden mathematical music plays. Discovery 10 reveals the gravitational dance of orbital resonance, a subtle order woven into the very fabric of these systems. Even with 9 stars pulling in every direction, astronomers have detected the faint, precise signatures of synchronized orbits. This occurs when the orbital periods of different pairs within the hierarchy lock into simple, clean ratios. Imagine one tight binary pair completes 2 full whirls around each other in exactly the same time it takes for that pair as a unit to complete 1 orbit around another stellar quartet. That is a 2-to-1 resonance, a cosmic clockwork where the gravitational pushes and pulls align in a repeating, predictable pattern. This resonance acts like a carefully timed push on a playground swing. If you push at just the right moment in the swing's arc, you add energy smoothly, maintaining a steady, high motion. Push at the wrong time, however, and you disrupt the rhythm, causing a jerky, unstable ride. In a Nonuple system, these gravitational pushes are constant, but when the orbits are resonant, those pushes arrive at the most harmonious points in each star's path, gently reinforcing the stable configuration rather than disrupting it. It is a self-correcting mechanism, a natural feedback loop that prevents the chaotic tugs from accumulating into a catastrophic shove. Without these resonant beats tying the chaotic movements together, the entire delicate hierarchy would unravel on a much shorter cosmic timescale. The system would drift into instability, leading to close encounters, violent ejections, or stellar collisions. So the survival of these families for millions of years is not just a matter of layered structure, but of rhythmic grace. It suggests that amidst the furious complexity, the universe still finds a way to impose a kind of elegant mathematical poetry, a silent symphony that keeps 9 suns in their precarious, beautiful balance. The mathematical harmony of orbital resonance suggests a stable design, but the universe has a secret to reveal about the true nature of these families. Discovery 11 uncovers a startling pattern in their cosmic addresses. Every single confirmed Nonuple system we have found is not drifting in the quiet, empty space between the stars. Instead, they are all embedded deep within the glowing, chaotic hearts of active star-forming regions. places like the vast Orion molecular cloud or the turbulent Taurus cloud. These are the universe's bustling stellar nurseries, immense clouds of gas and dust where new suns are being born by the thousands. This is not a coincidence, it is a critical clue to their age and their ultimate fate. Their location tells us that these 9 sun systems are cosmic infants, likely only a few million years old. In astronomical terms, that is the blink of an eye. We are not observing ancient, settled celestial kingdoms that have endured for billions of years. We are catching a glimpse of stellar adolescence, a brief and riotous phase of life immediately after a tumultuous birth. Within these dense nurseries, the raw materials for star formation are abundant, and gravitational encounters are frequent. This chaotic environment is the perfect crucible for building such complex hierarchies through a mix of simultaneous formation and frantic gravitational capture. But the implication is profound and a little melancholy. The breathtaking complexity we see is likely not permanent. These families of 9 may be inherently transient. Over the coming hundreds of millions of years, the same gravitational forces that built them will begin to dismantle them. The constant, subtle tugs from each member will slowly but surely perturb their delicate orbits. A close encounter between 2 widely orbiting groups could fling one star, or even an entire binary pair, out into the galactic darkness as a runaway star. Alternatively, a tightening orbit might end not in ejection, but in a violent merger, 2 stars colliding to form a single, more massive star. With each ejection or merger, the Nonuple system simplifies. A family of 9 might become a stable octuple, then a septuple, and so on until it settles into a less chaotic configuration, perhaps a quintuple or a quadruple system that can endure for much longer. We are privileged to witness these systems in their most spectacular and chaotic form, a fleeting moment of maximal stellar siblinghood. It makes you wonder how many of these magnificent families once existed in our galaxy's ancient past, only to have slowly unraveled into the simpler binary and triple systems that are more common today. Their rarity is not just a matter of difficulty in finding them, but a testament to their ephemeral beauty in the grand timeline of the cosmos. The brief, brilliant lives of these stellar families find a perfect parallel in a famous celestial landmark. Discovery 12 links Nonuple systems to a known class of cosmic wild youth called trapezium systems. The name comes from the iconic heart of the Orion Nebula, where 4 brilliant, young, massive stars form a rough trapezoid shape, bound together in a tight, chaotic gravitational dance. These are not the orderly, hierarchical systems we have been discussing, but something far more raw and unstable. They are stellar traffic jams, born from the densest knots within a collapsing cloud, where multiple massive fragments ignite almost simultaneously in terrifyingly close quarters. The theory suggests that a Nonuple system like HD 98800 might be an extreme high member count version of this phenomenon. Instead of 4 massive stars in a messy cluster, imagine 9. The dense core of a giant molecular cloud does not always form one star or even a tidy binary. Sometimes it fragments into a whole litter of stellar embryos, all condensing and igniting within a space not much larger than our own solar system. This creates an initial configuration of breathtaking violence. For the first million years, these young suns would whirl around each other in a seemingly random, chaotic scramble, their gravitational pulls constantly yanking their siblings into new, unpredictable paths. It is a stellar mosh pit of incredible energy. This initial chaos is critical because it is from this frenzied state that 2 possible futures emerge. The first is disintegration. Close gravitational encounters can act like slingshots, flinging stars out of the group at tremendous speeds, creating runaway stars that streak across the galaxy alone. The system sheds members until the remaining few achieve a stable, usually hierarchical arrangement. The second future is the one we are lucky enough to observe in Nonuple systems, a fragile victory of order over chaos. Through a complex series of gravitational interactions and perhaps a few ejections of the least bound members, the surviving stars manage to sort themselves into that layered, resonant hierarchy. They transition from a wild trapezium-style free-for-all into a structured, if still complex, celestial family. So when we look at a Nonuple system, we may be witnessing a cosmic metamorphosis in progress, a snapshot of a system that has just barely managed to avoid flying apart and is now trying to learn the delicate steps of a long-term gravitational dance. The light from a Nonuple system tells a story of constant celestial interference. Discovery 13 reveals the bizarre eclipses and chaotic light curves that act as the system's unique fingerprint. From our distant vantage point, the combined glow of 9 stars flickers and dims in patterns that defy simple explanation. This is not the clean, predictable dip of a single planet crossing its sun. Instead, imagine a cosmic stage with 9 actors where at any moment one might step in front of another, or even in front of a pair already dancing together. The eclipses are not singular events but overlapping symphonies of shadow. One star in a tight binary might be eclipsed by its partner, only for that entire whirling duo to then be silhouetted by a third star from a wider orbit. On rare, spectacular occasions, the geometry might align so that 2 completely separate eclipses happen at the same time, a double shadow cast across the entire system's light. The result, when plotted by our telescopes, is a graph of brightness over time called a light curve. For a calm, single star, this curve is a flat, steady line. For a Nonuple system, it looks like the frantic scribble of a seismograph during an earthquake, a jagged landscape of dips, bumps, and plateaus that seems like pure chaos. To the untrained eye, it is noise, but to an astronomer, every single wiggle in that line is a precious piece of data. Each strange dip reveals the diameter of a star sliding behind another. The shape of the dip's curve tells the temperature difference between the 2 bodies, whether a hot blue star is being covered by a cooler red one, or vice versa. The timing between these chaotic events slowly maps out the precise periods of the orbits, even for stars we cannot directly see. Decoding this requires immense computational power, running sophisticated models that simulate millions of possible configurations until one virtual system produces a light curve that perfectly matches the chaotic data from the real one. It is a monumental puzzle, but solving it gives us the system's portrait, a cosmic fingerprint of staggering complexity written in shadows and light. Decoding the chaotic light curve of a Nonuple system is one thing, but understanding how it was born is an entirely different cosmic mystery. The 14th discovery confronts us with the fundamental question of their origin, and astronomers are split between 2 equally dramatic theories. The first is the born-together scenario. Imagine a single, monstrously massive cloud of gas and dust, far denser than the typical stellar nursery. As it collapses under its own gravity, it doesn't simply fragment into 1 or 2 cores, but shatters into 9 separate knots of material almost simultaneously. These protostellar seeds ignite in terrifyingly close quarters, creating the initial chaotic scramble of a trapezium-style system. Through a violent gravitational sorting process where the weakest members are ejected, the survivors settle into the hierarchical dance we see today. This theory paints a picture of a single, explosive birth event, a stellar litter born from one exceptionally fertile cloud. The competing theory, however, is even more dynamic. This is the dynamic capture model. It proposes that the 9 stars were not born as one family, but as several smaller ones, perhaps a tight binary formed here, a triple system over there, in different parts of a bustling star cluster. Over millions of years, as these smaller families drifted through the dense cluster environment, their gravitational fields intertwined. A binary might swing too close to a triple, and instead of a chaotic collision, their motions perfectly align to create a gentle capture, binding the 2 groups into a new, stable quintuple system. This process repeats, with each gravitational encounter acting like a careful cosmic handshake. adding new members until the full Nonuple family is assembled. This is not a single birth, but a protracted construction project, a stellar family built through a series of fortunate and precise mergers. The evidence we have often tilts the scales toward the capture theory. Remember the extreme stellar diversity, the fifth discovery, where hot blue giants coexist with cool red dwarfs and even newborn protostars. Such a wide range of ages and types is harder to explain if all 9 stars condensed from the same cloud at the same time. A capture scenario, however, easily accounts for this menagerie, as it simply gathers stars that formed at different times and places. If true, this makes the existence of a stable Nonuple system not just rare, but almost miraculously fortuitous. It required a perfect series of gravitational interactions, each gentle enough to bind rather than destroy in a specific order within a specific environment. It suggests these 9 sun families are not just cosmic accidents of birth, but the universe's most delicate and unlikely sculptures assembled piece by piece across the eons. The chaotic light curves and competing theories of origin lead to one inescapable question: how can we possibly test which story is true? The 15th discovery takes us from the telescope to the supercomputer into the realm of n-body simulations. This is the ultimate digital laboratory for testing the stability of cosmic chaos. The N simply stands for the number of bodies, the 9 stars, each with its own mass, velocity, and position, all governed by Newton's laws of gravity. The problem is that for 3 or more bodies, there is no neat, single equation to predict their long-term fate. The gravitational influences are too intertwined, too chaotic. So astrophysicists turn to brute computational force, programming virtual stars with every conceivable starting arrangement and letting the digital clock run for millions of simulated years. The results are both humbling and illuminating. When they begin with random, plausible configurations, the outcome is almost always catastrophic. Within a few million virtual years, the delicate hierarchy shatters. A close encounter acts as a gravitational slingshot, hurling one star out into the void as a runaway. 2 others, their orbits twisted by the chaos, spiral inward in a fatal embrace, merging in a violent flash of simulated light. The system simplifies rapidly, shedding members until only a stable triple or quadruple remains. This digital carnage proves a profound point. The existence of a real, observed Nonuple system is not a random occurrence. It is a cosmic anomaly of the highest order. The simulations tell us that for 9 stars to hold together, their starting conditions must have been exquisitely precise, a gravitational needle threaded in a haystack of possibilities. Their initial positions, velocities, and masses had to align in just the right way to naturally settle into that protective, resonant hierarchy rather than explode into chaos. It is the difference between carefully placing 9 marbles on a taut, curved sheet and having them find stable resting points versus tossing them onto the sheet at random and watching them all immediately roll off the edges. These computer models are our window into that narrow path between a stable cosmic ballet and a gravitational demolition derby. They show us that the systems we see are the rare survivors, the lucky few whose initial tumble from the stellar cradle happened to be a perfectly coordinated fall. The violent chaos simulated by supercomputers is not just a threat to the stars themselves. Discovery 16 reveals the brutal influence of a Nonuple system on the very process of planet formation, turning what should be a peaceful construction site into a cosmic demolition derby. We know circumstellar disks exist in these systems, the raw materials are present, but the gravitational environment is a relentless, churning storm. Imagine a young, dusty disk encircling a single star within the family. As that star is constantly tugged by its 8 siblings, its motion is not smooth. It wobbles, it jitters, it speeds up and slows down along its complex path. These perturbations ripple through the disk like a series of gravitational earthquakes. For the tiny dust grains and rocks trying to gently coalesce into planets, it is a catastrophe. A forming protoplanet, perhaps the size of Mars, might find its orbit suddenly and violently altered. Instead of a gentle spiral inward or a steady growth, it can be flung completely out of the system at tremendous speed, becoming a rogue planet doomed to drift forever in the blackness between stars. Other unlucky worlds might be kicked in the opposite direction, sent on a death spiral directly into the fiery embrace of their parent star. Even if a planet avoids these fates, the chaos does not end. The gravitational stirring acts like a giant, invisible spoon, constantly agitating the belts of leftover planetesimals, the building blocks of worlds. This creates a state of perpetual, hyper-violent bombardment, where our own early solar system experienced a period of heavy impacts that lasted perhaps 100 million years. Here, that era never ends. Giant moon-shattering collisions would be a regular geological event, resetting the clock on any fledgling life or stable geology over and over again. The planets that somehow survive this gauntlet would be bizarre outliers. They might be ultra-hot, airless worlds scorched by orbiting far too close to their star for safety, tucked in the only gravitationally quiet zone available. Or they could be distant, frozen nomads on wildly eccentric orbits, swinging from the deep freeze of the outer darkness into brief, turbulent passages through the inner system. These would not be stable, life-nurturing worlds like Earth, but traumatized survivors of a gravitational war, their very orbits a testament to the relentless fury of their 9 suns. The gravitational violence that shapes planets also forges the very ingredients for new worlds. Discovery 17 reveals that Nonuple systems are not just chaotic families, they are prolific cosmic factories, enriching the space around them with the building blocks of future stars and planets. This process begins with the stars themselves, especially the massive, hot members common in these young groups. Burning through their nuclear fuel at a furious rate, these giants forge heavy elements in their cores: carbon, oxygen, silicon, and iron. In a solitary star, much of this processed material might remain locked inside for billions of years, but in the crowded, turbulent environment of a Nonuple system, it is expelled far more readily. The constant gravitational jostling can trigger powerful stellar outbursts, massive eruptions that blow huge plumes of this enriched gas into the void. More dramatically, the stellar vampirism and potential mergers we discussed earlier are ultimate recycling events. When 2 stars merge or one strips the atmosphere from another, they eject colossal amounts of stellar material, now laced with these newly forged elements, out into the surrounding space. This expelled material does not simply vanish. It is lit up and sculpted by the system's own intense radiation. The hottest, most massive stars in the family blast out torrents of ultraviolet light. This UV radiation acts like a cosmic blowtorch, heating the ejected gas and causing it to glow in brilliant, ethereal colors, potentially creating a small, private nebula that cloaks the entire stellar family. It can also evaporate nearby remnants of the birth cloud, carving out intricate shapes and cavities. But the most profound contribution is invisible to our eyes in the form of dust. As the ejected gas expands and cools, atoms of elements like carbon and silicon begin to stick together, forming microscopic solid grains. This stardust is the ultimate cosmic seed. Drifting away on stellar winds, these grains eventually mix with the wider interstellar medium, the thin gas that fills the galaxy. They enrich it, making it dirtier and more fertile. When this enriched material collapses to form a new generation of stars and planets, those new systems will start with a richer supply of heavy elements. This means that the violent, short-lived chaos of a Nonuple system directly contributes to the creation of rocky planets like Earth and the complex chemistry necessary for life elsewhere. Their spectacular lives end as a gift to the galaxy, a legacy written in atoms forged in fire and scattered by gravitational storms. This stellar enrichment is not just a byproduct, it is a direct window into the physics of stars themselves. Nonuple systems function as a laboratory for extreme stellar evolution, a place where nature runs experiments we could never replicate. We cannot place a star in a jar and subject it to intense gravitational stress, but the universe has conveniently built these 9 sun families where that stress is a constant defining feature. For astronomers, this is a priceless observational testbed. Every theory about how stars age, from their fiery youth to their final, fading embers, is based on models of isolated stars or simple binaries. But what happens when a star's entire life is spent in the relentless gravitational grip of 8 siblings? The questions are profound. Does the constant tidal flexing from nearby companions, a kind of perpetual gravitational massage, churn a star's interior enough to mix fresh hydrogen into its core? This could effectively refuel the star, causing it to burn hotter and longer than a solitary star of the same mass, subtly altering its expected lifespan. Conversely, could the same forces disrupt the delicate balance in a star's core, accelerating its nuclear burning and causing it to exhaust its fuel prematurely, like a candle guttering in a strong draft? Even more dramatically, these systems force us to reconsider stellar death. A massive star is destined to end its life in a supernova, a titanic explosion that seeds the galaxy with heavy elements. In a crowded hierarchy, the final moments of such a star could be catastrophically influenced. As a massive star nears the end of its life and begins to swell into a red supergiant, the gravitational pull from a close binary partner could begin to strip away its outer layers prematurely. This theft might alter the very mechanics of the core collapse, potentially leading to a different type of supernova than we would predict. Or imagine the gravitational shockwave from one star going supernova, rippling through the delicate orbital balance of the entire family. That cataclysmic event could trigger a chain reaction, destabilizing other massive members and hurling them on new, dangerous paths, perhaps even inducing a second supernova sooner than nature intended. By observing the diverse stellar populations within a single nonuple system, comparing the apparent ages and behaviors of stars that were likely born together, astronomers can see the deviations. They can spot the blue straggler that looks too young, or the massive star that seems poised for an unnaturally early demise. Each anomaly is a data point, a clue to how gravity not only shapes the dance of stars, but also the internal fires that define their very lives. The gravitational slingshot that can doom a planet has an even more dramatic effect on the stars themselves. Discovery 19 unveils a direct link between these chaotic families and the galaxy's most solitary and speed-blurred travelers, the runaway stars. The same N-body simulations that predict the fragility of nonuple systems also reveal their most common form of decay, the violent ejection of a member. In the crowded core of such a family, a close 3-body encounter can act as a perfect cosmic catapult. 2 stars swing close together, their mutual gravity forming a temporary slingshot that hurls the 3rd star away with incomprehensible force. We are not talking about a gentle nudge out of orbit. These ejections can accelerate a star to hundreds of kilometers per second, a velocity so great it can overcome the gravitational pull of the entire galaxy. This creates what astronomers call a hypervelocity star, a lone sun streaking through the interstellar darkness on a one-way trip out of the Milky Way. For years, the origin of these extreme speedsters was a mystery, often attributed to interactions with the supermassive black hole at our galaxy's center. But the physics of dense, high multiple systems provides another compelling nursery for these runaways. A star ejected from a disintegrating nonuple system would carry an invisible but telltale signature, the precise chemical composition of its original stellar family. Its atmosphere would be a time capsule, holding the unique blend of elements forged in that chaotic, shared environment. By analyzing the light from a hypervelocity star, astronomers can read this chemical fingerprint. If they find an abundance pattern that matches young, massive stars, but the star itself is now racing through an old, quiet region of the galaxy, it becomes a powerful clue. This star might be an escapee, a survivor cast out from a spectacular breakup that occurred millions of years ago in a distant stellar nursery. It is a ghost from a vanished family, its incredible speed the only remaining testament to the furious gravitational drama of its youth. Every hypervelocity star we find could be a clue pointing back to a catastrophic event, the moment a family of 9 suns became 8 or 7, and sent one of its own on a permanent, high-speed exile into the galactic night. This glaring absence of ancient families points to a fundamental truth about their nature. Discovery 20 confronts us with the mystery of the missing older Nonuples. Every single one of these 9 sun systems we have catalogued is a cosmic youth, less than 100 million years old and still nestled in its dusty stellar nursery. If these hierarchical arrangements were truly stable for the long haul, capable of enduring for billions of years like many binary stars, we would expect to find them scattered throughout the older, quieter regions of the galaxy, in places where star formation ceased eons ago. We do not. Their complete absence from the galactic suburbs and ancient star clusters is a silent but powerful statement. It suggests that the breathtaking order we observe is a temporary illusion, a delicate configuration that cannot withstand the slow, relentless grind of time. The gravitational perturbations, no matter how minimized by hierarchy and resonance, are like a constant, whispering erosion. Over hundreds of millions of years, these tiny effects accumulate. A slight wobble in a wide orbit grows larger. A close encounter between 2 of the outer groupings, once every few million years, eventually delivers a gravitational kick just a little too strong. The system does not necessarily explode in a sudden catastrophe. Instead, it undergoes a slow, graceful decay. The most loosely bound pair or quartet at the outermost layer of the hierarchy might gradually drift away, its connection to the core family severed by the accumulated nudges from its siblings. What was once a nonuple system could peacefully separate into 2 smaller, more robust families, perhaps a stable sextuple and a triple, each going their own way through the galaxy. Alternatively, internal mergers might reduce the head count, simplifying the dance until it reaches a stable lower number. The nonuple systems we are lucky enough to observe, then, are not enduring kingdoms. They are fleeting cosmic fireworks, brilliant and complex structures shining at the peak of their complexity during the brief era after their formation, before time and gravity inevitably begin to simplify them. We are witnessing a transient state of maximal stellar siblinghood, a spectacular but doomed arrangement in the slow-motion story of gravitational evolution. The light from these stars holds a detailed chemical confession. Discovery 21 examines the peculiar abundances within their atmospheres, where the story of their violent lives is written in the language of elements. By splitting the starlight into its component colors, a technique called spectroscopy, astronomers can read the unique fingerprint of every atom present. In calm, isolated stars, these chemical signatures are predictable, reflecting the composition of the primordial cloud from which they formed. But within a nonuple system, the rulebook is torn apart. Researchers have observed stars with bizarre overabundances of specific elements, like lithium or barium, elements that should have been burned away in the star's core or were never present in such quantities at birth. This is the indelible mark of the system's intimate chaos. One clear source is the stellar vampirism we witnessed earlier. When a star siphons the atmosphere from its companion, it is not just stealing hydrogen. It is also stealing every element that companion has cooked up or collected in its outer layers. If the donor star had previously enriched its atmosphere through internal processes, that contamination is transferred directly to the surface of the receiving star. The recipient spectrum suddenly shows a spike of an element it could not possibly have produced on its own, a permanent chemical tattoo from a cosmic theft. But there is another, more subtle pathway. Imagine the dusty debris disks that perpetually grind within the system, the remnants of countless collisions. This dust is not pristine. It is laced with the heavy elements forged in supernova or expelled from stellar mergers that occurred earlier in the system's violent history. When a star plows through this enriched debris, it can accrete this contaminated material directly onto its surface. The star's outer atmosphere becomes polluted with the ashes of its siblings' cataclysms, its light telling a story of cannibalized planets and long-vanished stellar explosions. In this way, each star's spectrum becomes a layered history book. By comparing the chemical stories of all 9 members, astronomers can attempt to reconstruct a timeline of past events. Which star shows signs of mass transfer? Which one is covered in the dust of a recent planetary demolition? The answers are not just in their orbits, but in the very atoms that compose their light, a permanent record of the shared violence that defines their existence. These chemical tattoos of violence are mirrored by a different kind of chaos entirely, one found not in the stars but in the paperwork. Discovery 22 reveals the wonderfully strange bureaucratic nightmare of simply naming these stellar families. For a single star, we give it a catalog number or a proper name. For a simple binary, it is star A and star B, a clean and elegant solution. But what do you do with 9? Astronomers have devised a hierarchical naming convention that, while logical, becomes a tongue-twisting reflection of the system's own physical complexity. It starts with capital letters for the widest orbital pairs, so the first binary you identify might be component A, but inside that component A there are 2 stars. Those become R and AB. Now, imagine component A is actually a binary pair orbiting another binary pair, which is component B. The stars in component B become Ba and BB. If one of those, say Ba, is itself a tight binary, you now have stars named Ba and Bab. The names can cascade into a nearly alphabetical absurdity. A real-world example is the stunning system Nu Scorpii, which from Earth looks like a single bright point but is actually a septuple system of 7 stars. Its official designation reveals the layers. Nu Scorpii itself is a triple star, often labeled as A, B, and C. But component A is a spectroscopic binary, meaning its 2 stars are too close to see separately, so they are R and AB. Component B is also a close binary, Ba and BB, and component C is yet another binary, Ka and CB. So the full family is R, AB, Ba, BB, Ka, and CB, with one more star sometimes included in wider orbits. Trying to say that aloud feels like reciting a cosmic nursery rhyme gone wrong. This naming chaos is not just an amusing clerical detail. It is a direct linguistic echo of the gravitational reality. The nested R and AB names on a page are a perfect map of the nested orbits in space. The complexity of the notation forces your brain to visualize the hierarchy, to see that Ba is a star deeply buried within a subsystem, orbiting a partner before that whole unit engages in a wider dance. In a very real way, the unpronounceable name is the system's truest label, a testament written in letters to the breathtaking, layered madness that defines its existence. The delicate web that binds 9 suns is woven from a terrifying vulnerability. Discovery 23 forces us to confront a potential doomsday scenario, the threat of a supernova chain reaction. Within the tightest binary pairs at the heart of the hierarchy, a star reaching the end of its life does not die quietly. It explodes as a supernova, an event of almost unimaginable violence that releases more energy than our sun will in its entire 10 billion-year lifetime. In an isolated binary, this often severs the gravitational bond, sending the companion star and the supernova remnant flying apart. But place that binary within the intricate gravitational lattice of a nonuple system, and the consequences could be apocalyptic for the entire family. The explosion is not just a flash of light, it is a fundamental restructuring of the system's mass and momentum. In an instant, one of the most massive objects in the local hierarchy simply vanishes. Its remains reduced to a dense neutron star or black hole carrying only a fraction of the original star's mass. This sudden, catastrophic loss of gravitational anchor is like cutting the central cable on a suspension bridge. The intricate balance of forces that maintained every wider orbit is instantly shattered. The surviving companion in the binary is not just freed, it is given a ferocious kick by the shockwave and asymmetrical blast of the explosion, becoming a runaway projectile within its own family. This stellar shrapnel now hurtles on a new, chaotic path through the heart of the system. It could slam directly into another star, triggering a titanic merger. More likely, its new trajectory brings it perilously close to other tight pairs or stellar groupings. These close gravitational encounters act like cosmic pool shots, scattering other members onto new, unstable orbits. The entire hierarchical order, painstakingly maintained for millions of years, unravels in a cosmic instant. The chaos does not end there. If the system contains other massive stars already on the brink of collapse, the gravitational pandemonium could be the final push. A close pass from the runaway star could compress a giant's core or strip its outer layers in a violent tidal interaction, hurrying its demise. One supernova could thus trigger a second, and then perhaps a third, in a cascading stellar catastrophe. The Nonuple system would transform from a ballet into a demolition derby, a fireworks display of colliding stars and sequential supernova visible across the galaxy. While we have not yet witnessed such an event, the physics is chillingly plausible. It means that the greatest threat to these complex families may not be the slow erosion of time, but a single, violent death from within. The ultimate fate of a Nonuple system may be a cascade of stellar explosions, but its intricate dance also offers a chance to test the very fabric of reality. Discovery 24 suggests these families are nature's most complicated gravitational clocks, and they could become the ultimate laboratory for probing Einstein's theory of general relativity. In our solar system, the subtle effects of gravity are gentle. Mercury's orbit precesses, its elliptical path slowly rotating around the Sun by a tiny fraction of a degree per century, a perfect match for Einstein's predictions. But within a Nonuple system, the game changes entirely. Here, especially in the tightest binary pairs, stars whirl around each other at incredible speeds in immensely strong gravitational fields. In this environment, the effects predicted by general relativity are magnified 1,000-fold. The precession of such an orbit should not be a subtle drift over a century, but a potentially observable shift over just a few years. The entire orbit itself might rotate like a spirograph drawing in the sky. Tracking these hyper-fast, complex motions with extreme precision over decades could reveal something extraordinary. If the observed precession matches exactly what general relativity calculates, it would be a stunning confirmation of the theory in a regime of gravity we have never been able to test so severely. But what if it does not match? A tiny, persistent deviation in the timing of eclipses or the wobble of a star could be the first whisper of new physics. It might hint that our understanding of gravity, while brilliant, is still incomplete, that in these most extreme gravitational furnaces, Einstein's equations need a slight, revolutionary adjustment. These 9 sun systems, with their nested orbits acting like interlocking gears in a cosmic timepiece, offer a precision we could never engineer. They are the universe's own gift, a chance to read the deepest rules of space-time written in the frantic motion of stars under unimaginable strain. This final discovery is perhaps the most humbling of all. For centuries, we have gazed at our own solar system and assumed its quiet solitude was the cosmic standard, a single star presiding over a family of planets. But the existence of Nonuple star systems, these fragile, chaotic, and breathtakingly complex families of 9 suns, forces a profound shift in perspective. It reveals that our Sun, with its orderly planetary procession, might not be the rule but a peaceful exception. In the grand tapestry of stellar arrangements, our neighborhood is the quiet suburb, while the universe's nurseries are bustling metropolises of gravitational interaction. We have learned that binaries are common, triples and quadruples exist in surprising numbers, and now we know that nature, under the perfect conditions of density and chaos, can architect systems of 9. This is not a fluke or an error, it is a demonstration of the universe's boundless creative potential. The cosmos operates under a set of physical laws, but within those laws, it has an almost artistic license to experiment. Gravity, nuclear fusion, and angular momentum are its paints, and it can paint anything from a minimalist portrait of one star to a Baroque masterpiece of 9. These systems challenge our very definition of stability and order. We thought stability meant simplicity, a clean, predictable orbit. But Nonuple systems teach us that stability can also be a fantastically complex, layered, and resonant dance, a precarious piece maintained not in spite of chaos, but by organizing it into a fragile, hierarchical symphony. They expand our imagination of what is possible. If 9 stars can find a way to coexist, what other architectural wonders does the universe contain that we have not yet dreamed of or lack the patience to see? Every time we push our instruments further and stare a little longer, the cosmos responds not with simplification, but with deeper, more intricate layers of wonder. It reminds us that our quest to understand the stars is not about fitting them into our existing boxes, but about allowing their light, in all its bewildering complexity, to teach us how many boxes we have yet to open. From gravitational ballet to cosmic chaos, these 25 discoveries paint a picture of Nonuple star systems as some of the most extreme and fascinating laboratories in the galaxy. They are not just curiosities, they are fundamental challenges. Each one forces us to rewrite our models of stability, to reconsider the timelines of stellar lives, and to accept that planets can form in environments we once thought were pure gravitational anarchy. They dazzle our imagination with visions of skies filled with multiple suns and climates that shift over geological ages. More than anything, they are a masterclass in cosmic humility. Just when we think we have mapped the rules, the universe unveils a system of 9 stars dancing in a fragile, resonant order, proving once again that reality is always stranger, more creative, and more wondrous than we can suppose. If you found this journey into multi-star madness as thrilling as we did, smash that like button, subscribe for more deep dives into cosmic mysteries, and let us know in the comments, which of these 9 sun wonders blew your mind the most? Was it the stellar vampirism, the hypervelocity runaways, or the sheer impossibility of their temporary peace? Until next time, keep looking up.